So let's go ahead and take a look at this problem here. So first of all, 71.6%, what's that in a decimal? 0.716. Everybody on board with that part? Okay. All on time. That means that he took a flight, it was on time. She took a flight, it was on time. She took a flight, it was on time. What's probably his flight was on time? 71.6. Yeah, 71.6%. What's probably her flight was on time? 71.6. What's probably her flight was on time? And now I find the probability that his was, and hers was, and hers was, and we multiply. Thank you. And we multiply, so this would be 0.716 times 0.716 times 0.716. On your calculators, incidentally, you can have a little caret number, so it looks kind of like this, raised to the third power. That's what that does. And what do you guys get for that? 0.3. I'll write it the other way first, so people get confused. 0.367? 67? Okay, great. None were on time. So none were on time means that, what's probably that he takes a flight and it's not on time? What's probably the flight is on time? 0.716. So the probability that it's late is what? 1 minus 0.716, which is, what'd you guys say? 284. Great. So it's probability that his flight is late. Not a trick question. His flight's late. What's the probability of that? 0.284. What's probably her flight's late? 0.284. What's probably her flight's late? So probably his is and hers is and hers is, and we multiply. You guys, are you just really tired or what?
It was like a Wednesday.
Yeah, I guess so. Raised to the third power. And you guys got 0.0023. Incidentally, let's take a look at this real quick.
One day for kidney, I might say right, that's one. Right?
So, if I want to raise a number, so say I have 0.023 raised to the fifth power. So if I want to raise it, 0.023, if you need to raise it to an exponent, this little guy right here is the raising to button. It raises it to the whatever power. So raise it to the fifth power. See where it says 6.43? It is not 643%. Right? We all know you can't be more than 100%. So if you have a number greater than 1 there, then there darn well better be an E negative something at the end. So here, it's E negative 9. That means you move the decimal place over 9 times, should become smaller or larger? Smaller. Negative, make it smaller. The easy way to do this, one of my students said, was just take, here I'll show you. If I have 4.28, blah, 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 E negative 4. Put 4 zeros in front. 1, 2, 3, 4. And decimal place goes after the first 0. That's it. That's the fastest way. Or you could just count over 1, 2, 3, 4. But you do this after the first one. You just put 4 in front. Really clean, really easy. All right, so this one, at least 1 was on time. So at least 1, the complement of at least 1 is none. Thank you. So at least 1 was on time. The easiest way to do this is to just take this 1 and make it none. So put an N here. None was on time. If none was on time, that's this guy here. Or maybe you have to wrap your head around and say none were on time. That means all were late. and kind of work it that way, because some of them are a little bit trickier word-wise. Like, none were girls really means all were boys, right? So this is 1 minus probability none was on time. I know my English is bad there, but I just want to copy it over verbatim. Just add the N in front, right? That's the complement. At least one, none. Complement. So that's going to be equal to 1 minus 0.023, which is 0.977. Good?
Yes.
Great. All right. Quick comment about law of large numbers. Okay, so the first one is, why am I reading? I would like someone else to read. How about Brendan, go ahead. You guys, I can't hear him. Good? Yeah.
If you flip a coin 10 times, you expect 5 heads, but very often you will get 4 heads, or 6, or some other number. This is just due to randomness. The law of large numbers states that as you perform an experiment, like flipping a coin, as your sample size increases, the observed probability will get closer to the true probability.
Yep. So that just says as you keep doing it more and more often, you're getting closer and closer to 50%. Right? If you're only doing it 10 times, if you only do it twice, you might get 100% one way or 100% the other way, right? If you do it 10 times, then you might get something more like 60, 70% one way or 30, 40% the other way. If you do it 100 times, you're going to get more like 55% or 60% one way and 40% the other way. If you do it 10,000 times, you might get like 52% to like 48%. It's going to become, the variance is going to become less and less. What this does not mean is that if a coin has come tails, 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 that's more likely to come heads the next time. Because every single flip is still 50-50. The coin doesn't know that, oh, well, I came tails last 4 times, I better come heads. It has no memory at all. Right, so each coin flip is still back to that 50%. So the moral of the story is if you go to the casino and I should tell you my story. So I played Baccarat, my second time playing Baccarat. After that, I didn't play for a very long time. I bet $25 on Banker. I lost. Okay, no problem. I'll put another $25 on Banker, try to get my money back. I lost. All right, so I'll make it $50 on Banker. Can't 3 times in a row. Lost. $100 on Banker to get my money back. Lost. $200 on Banker. Lost. $400 I lost because it can come banker, 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 banker sometimes. Right? So I just lost $400, which really hurt. Sorry. What was that?
What was the next one, Baker?
I have no idea. I didn't even care. I walked away. You don't want to look. You never want to look. Yeah, so just remember, the house always wins. They just do. That's the whole point of probability. Remember, is they do. All right, so everyone bust out your notes and turn to the next page. We are, or the bottom of that, sorry, maybe the bottom of that page. Hold on. Let's see where you're at. Yep, next page. Bottom of the next page. A couple pages over. All right, so let's do it this way. If you're looking at the very back, look at the back. Flip 1 page up. And it's right here. That's what we want, at the very bottom. Counting chapters 4.4, 4.5. That's what we want, right there. Good? All right, so fill in your first blanks. And let's have Soraya, go ahead and read.
The fundamental principle of counting. The total number of possible outcomes of a series of decisions is found by multiplying the number of choices for each decision. Example, 2 pants, 3 shirts, 5 shoes, 4 socks. How many possible wardrobe combinations?
Right, so you can multiply them. 2 times 3 times 5 times 4. This is the exact same thing we would get. Sorry. This is the exact same thing we would get if we were drawing a tree. Only if you drew a tree diagram, it would take a lot more work. Right? So we could do like the first layer of branches would be pants, and second layer of branches would be shirts, and third layer of branches would be shoes. I'll show you the first couple layers what that would look like. Right? So I have 2 choices for pants, jeans or slacks. No matter which one I pick, I have 3 shirts. Right? So I have I have a group of 3. How many groups of 3 do I have? 2, because there's 2 things here. Then my next thing is what? 5 shoes? 1, 2, 3, 4, 5. So I have this kind of branch with this thing of 5 branches. How many groups of 5 do I have here? How many groups of 5 am I going to have? I got 1 there. 6. 1, 2, 3, 4, 5, 6. Why are there 6? Because I have a group of 3 times a group of 2. Right? So I have 6. So that's where this came from. There's 6 of these because 3 times 2 makes 6. Everybody, is that making sense to everybody? All right. So then 5 of those, 5 times 6, 30. And then you have, and so on as you kind of have more, and you have your socks after that. So you guys try. It's not on your sheet. You guys just look at this with your partners, figure out what this is. 30 seconds, go. Okay, so how many options for pants? How many options for shirts? Shoes? Socks? What are you going to do with those all? Multiply them. Great. So shortcut, obviously take your 2 and your 5 first. That makes 10. 6 times 3 is 18. And then add a 0 for the 2 and the 5. On a test, how do you know to multiply instead of add? You can just make yourself a little tiny tree with like 2 pants and like 3 shirts or 4 shirts. So 2 pants, 4 shirts. I end up with 1, 2, 3, 4, 5, 8. And how do I get from 4 and 2 to 8? Do I add them? No. So I'll multiply them. So then you know it's multiplied, right? Kind of to help yourself remember. Do problem 5 on your lab. So, not the one on the page. Flip the page and do the next one. Unfortunately, I have 2 number 5s.